Okay, hi everyone. So today we're having a guest lecture from Ilya Rosenstein, who's joining us from Microsoft Research in Redmond. Before I hand it off to him, I just wanted to say some logistical things. I did release problem set 1 this past weekend. You can find it on the website. You do need to enroll in the Gradescope to submit. Everyone should have gotten an email with the enrollment code for Gradescope. If not, please send me an email. Second thing, final project proposals are due October 28th, which is in a little over 3 weeks. You are allowed to do these in teams. Go to the course webpage for instructions on how to prepare your proposal and submit them. If you have some questions, feel free to come to my office hours, or if you can't make those, set up a time with me to talk about what you're thinking about for the project. And now we're going to have Ilya talk about a result of his from a few years ago. So we've talked about sketching and streaming various norms like the Euclidean norm and other LP norms. Ilya is going to talk about a pretty general theorem that relates embeddings and sketching for norm spaces. So thank you, Ilya, for joining us today.
Thanks, Jelani, for the introduction. So as Jelani said, I will talk about our paper that we had a few years ago that shows that basically d-dimensional norm has a good sketch if and only if it nicely embeds into a certain sufficiently simple space. So even though Jelani asked me to present like as much proofs as I can, I will not be able to show you all the proofs, but I will show you proof of like big chunk of the result. But before I'll talk about the result, let me briefly, even though you have seen some streaming and sketching in this class, let me briefly reintroduce it, tailored to this specific lecture. So let's briefly recall what is sketching. So you have some metric space, which can be finite or infinite. So it's basically some set X equipped with some distance function d sub X. And we basically would like to solve the following communication problem. We have Alice and Bob. Each of them both of them have a point from our metric space, and then they would like to talk to each other, exchange S bits of information, and later decide whether points are close or they are far. And basically, they know a priori that either the distance is at most 1 or the distance is more than capital D. And they would like to tell apart these two situations. There are like a few subtle points in this model. So for now, I just introduced it in a fairly hand-wavy way. But there are like a few important things that are important for the result I'm going to talk about. But we will not be like basically, yeah, it will not be super important for the lecture, but it is important for the result. So basically, the nuances of this model are what coins do we allow and how many of them. So basically, if the protocols are randomized, and we allow randomized protocols because they are more powerful and they actually give us lots of leverage, as you have seen in previous lectures. But the subtle point is whether coins are public or they're private. What does it mean? So when coins are private, it means that Alice has her own source of randomness and Bob has his own source of randomness, and they just send messages based on this randomness that they own. A more powerful model is public coins, when actually Alice and Bob have common source of randomness that both of them see, and this allows them potentially to agree on certain things without even communicating anything. For this result, it will be important to allow not only public coins, but to allow countably many of them. So what does it mean? It means that not only we have like, access to just like, maybe some finite number of public random coins, but we assume that we have access to the whole sequence of random coins. So basically they're indexed by, say, positive integers or something like this. And both Alice and Bob can use them to base their decision on them. And why do we need countably many coins? Because we want to operate with such things as Gaussians or some other continuous random variables, which require countably many discrete coins to actually even produce a single sample, right? So countably many public coins is not the usual notion of communication protocol that is usually considered in the computer science literature. But because our upper bounds are in this model, we need to work with this model. But again, for the sake of this lecture, it's not super important. Just like keep in mind that we have public coins and there are many of them. So that's it. And since we allow randomized protocols, we just require, as always, that success probability is at least 2/3. So basically, if distance between 2 points is small, then with probability 2/3, they say that the distance is small, and vice versa. Okay, so that's roughly the model. So let's see what we can do in this model. Of course, we can handle finite metrics, right? So for any finite metric space, there is a protocol in this model. It can even achieve. So basically, I'm going to refer to this. Let me rewind a little bit. So I'm going to refer to this quantity S as like sketch size, or like communication protocol size in this case. And I'm going to refer to D as like approximation. So for finite metric space, we can obtain any approximation more than one, right? Just because the metric is finite, we can pretty much send the whole point, right? But what can we do besides finite metrics? So the first thing is, suppose we have, suppose that our metric space is just d-dimensional Euclidean space, then what can we do? So Alice and Bob now have d-dimensional vectors. Each of the vectors consists of real numbers. Turns out that then the following protocol works. Again, you have seen it in previous lectures, but I'm just gonna remind you a certain version of it that works in this precise model, where we like fix how many bits we would like to exchange rather than like, so we don't want to cheat saying that, you know, we exchange real numbers because each real number has like infinite number of information, infinite amount of information. So we will be pedantic and we will want to talk about like exchanging bits proper, right? Okay, so basically how can we design a good protocol for the Euclidean space? So they need to sample D independent Gaussians using common randomness that they have, public randomness. And then they need to obtain basically fold the vectors using these Gaussians. So obtain these numbers x tilde, y tilde, which is just dot product of this Gaussian vector with their products. And now the intuition is that difference between x tilde and y tilde should give us a pretty good idea what the L2 norm between x and y is. So specifically how we go about it is we basically, so we would like to estimate the difference between x tilde and y tilde, but it's also not very clear how to do, because these are, again, these are real numbers. We don't want to send them. We want to do something with them, you know? So the solution turns out is pretty simple. So we just take our real line on which these numbers are situated, located, and just basically randomly partition it into windows of size W, where W is a certain parameter. And then we color each of these windows in random plus minus one. So all of that can be done using public randomness. So we can sample where to start our random partition. This is random number between 0 and W. And then we basically can use countably many coins to basically assign this random plus minus ones. Yeah, so then what do? We basically, like, Alice locates x tilde on this line, and Bob locates y tilde on this line. And then they obtain the respective plus minus one, right? And then they basically exchange these plus minus ones, and then they say that their vectors are closed if and only if these plus minus ones are the same. So basically, if both of them got plus one, then they say it's closed. If both of them got minus one, then they say it's closed. If one of them got plus one, another got minus one, then they say that it's far. So let's analyze this protocol. Again, I'm going to be quite brief here, but let me just say that the intuition is that basically if distance is close, then probability that if you choose this window size carefully, then the probability that x tilde and y tilde end up in the same bucket is non-trivially higher than for the case of far points. Actually, I have inequalities messed up here, so they should be, I believe, the other way around. So they should be like, basically, if the points are close, then probability of collision is at least something, and if the points are far, then the probability collision should be at most something. And the point is basically epsilon1 is noticeably higher than epsilon2 if we choose window size correctly. So basically epsilon1 minus epsilon2 is omega of epsilon, right? So that, I mean, that's pretty like, that's intuitively clear, right? So basically if your vectors are short, then when you take a dot product of them with Gaussians, then you will obtain Gaussian with basically slightly lower variance than in the far case. And that's how you get this separation. So basically the probability of our test saying close will be like non-trivially different in both of these cases. And we can amplify it to, again, sorry, I have inequalities messed up here. This is just matter of animation. But this probability of success can be amplified to 2/3 using around 1 over epsilon square repetitions and just like doing majority voting. So if you didn't understand what I'm talking about, let me just say that one line of it is we take this sketch using Gaussians and just discretize it using this trick of coloring line in random colors. And we need this discretization just to talk about, you know, sending bits rather than sending real numbers or sending integers or something. But the punchline here is that for every epsilon larger than 0, we can obtain approximation 1 plus epsilon with sketch size 1 over epsilon squared. And we can do the same for LP distances where P is at most 2. Just instead of Gaussians, you need to use p-stable random variables. Otherwise, the protocol and analysis are exactly the same. And the result you obtain is also exactly the same. So you obtain 1 plus epsilon approximation with sketch size 1 over epsilon squared, protocol size, whatever. Okay, so now we get our result. We get to our result. So what's our result? Basically, if you have finite dimensional normed space, and for this finite dimensional normed space, there exists such a protocol as I described. So basically like communication protocol with exchanging S bits and obtaining approximation D, so telling apart distances at most 1 versus more than D. Then there exists an embedding of this normed space, a linear embedding, into L1 minus epsilon space. And the distortion of this embedding is protocol size times protocol approximation divided by epsilon. So what the hell is this L1 minus epsilon, and why do we care about such a result? So L1 minus epsilon, so this is like LP space for p smaller than 1. It's not even a normed space. It's not even a metric space because it doesn't satisfy triangle inequality. But nevertheless, this space is still useful because actually for this space, you have good sketches. So again, p-stable random variables exist even for p smaller than 1. So basically for L1 minus epsilon, you can get good sketch with very good approximation. So basically this result gives a characterization. So norm allows a good communication protocol for the sketching problem, for distance estimation problem, if and only if it embeds into like particular space that is easy to sketch. So basically in some sense, this is a complete problem in this sketching, so to say. By the way, any questions about the result? Do you even follow me? Do you?
I mean, so the SD protocol is the thing you described at the start of deciding like the distance is bigger.
Yeah. So what's the question? Sorry.
I guess.
Okay. So maybe. Yeah. Yeah. Okay. Okay, so let me give a few comments about this result. First of all, it's formulated for normed spaces, but you may hope for this result to hold for general metrics, not only for norms. So it turns out that this is false for general metrics. Also, like certain examples demonstrate that this SD bound is tight, so you cannot improve. So for example, you cannot prove bound like square root of SD. So basically you really need this S times D. But what is not clear, and what's an open problem, though likely it's a hard problem because it's equivalent to certain known hard problems in mathematics, but a priori it might it still might be true that actually this theorem holds with L1 minus epsilon replaced with L1. for this L1 case, we can actually also obtain certain result, but then the distortion that you obtain for embedding into L1, it would depend on the dimension of your norm space. So it would be something like SD times log of the dimension of your norm space. Whether you can obtain dimension independent bound like this, that's an open problem. So I don't know what the answer is. Okay, so like, why do we care about something like this? Because it allows us to show lower bounds for communication protocols or for sketches. So basically, so I showed you that if communication protocol exists, you can obtain a certain nice embedding into a sufficiently nice space. So if you take this result in the contrapositive, then you will get that if embedding doesn't exist, then there is no communication protocol. And this is a very nice implication, because non-embeddability results, they are much easier to prove than communication lower bounds, because embeddings, intuitively speaking, because embeddings are much more regular objects, linear embeddings specifically. So we obtain certain new lower bounds. Again, I'm not going to talk too much about them, but basically both of them are still state of the art. Sorry, again, like this slide is wrong. So they should be communication lower bounds from embedding lower bounds, not sketching lower bounds. Okay, but this is so the lower bounds for communication we are getting are for spectral norms, or sorry, not spectral norm, my bad. Schatten-1 norm or trace norm, which is basically just sum of absolute values of eigenvalues of say asymmetric matrix. And then the second norm for which we obtain a new lower bound is Earth mover distance. So again, intuitively, this is just like if you are on the plane, you can consider sets of like n blue versus n red points. And then the distance between these sets is defined as minimum cost perfect matching, where underlying cost is just Euclidean distance on the plane. And then it can be turned into a normed space if you allow like weighted sets or whatever, not super important. But then for this normed space, we actually obtain first non-trivial communication lower bound for our distance estimation problem.
Sorry, Ilya, just to make sure I'm not misunderstanding. Did you mean embedding lower bounds from sketching lower bounds, or did you mean?
Yeah. I mean sketching lower bounds from embedding. So they
sketching lower bounds from embedding lower bounds. Okay.
Yeah. So basically, we take existing non-embeddability results and just use our theorem in more or less a black box way, and just obtain communication lower bounds. Because if there would be a good protocol, then there would be good embedding. But embedding doesn't exist by known theorems. So yeah, that's the primary application. But also, I think this is just like, philosophically reasonably interesting that the only way to obtain good communication protocols for distance estimation problem for normed spaces is to just embed them into L1 minus epsilon or L1 and use p-stable random variables. So basically this like sketching using p-stable random variables, in some sense, it's the universal way of sketching distances if your metric space is a norm space. I think it's pretty interesting. Okay, so let me talk about the proof. So basically the proof consists of two big parts. I'm gonna give you almost the full proof if time permits of one of these parts, but not the other one. So basically the starting point is we start with this SD protocol as I defined in the beginning. And then we obtain certain embedding, but not what we actually want in the end. This will be much weaker object. So what is this object? So basically it's an embedding of our space into a Hilbert space. Hilbert space is roughly speaking like infinite dimensional analog of L2. So let's, for the sake of this lecture, abusing notation, let's just think about L2. It's not quite L2, but it's kind of like infinite dimensional L2. So basically we obtain a map from our normed space into L2. It doesn't have to be linear, but what we do require is that for every 2 points, basically short distances get mapped into short distances and large distances get mapped into large distances. So basically distances at most 1 turn into distances at most 1, and distances at least 100 times SD turn into distances at least 10 in the image. So this is much quicker than we want because this just works for a single distance scale. And because this is not a linear embedding, it doesn't have to work for other distance scales. But then we use geometry or some like geometric and analytic arguments and obtain what we want. So then we kind of like regularize this mapping and make it nice and linear and turn it into actual linear embedding into L1 minus epsilon with distortion. So all distances get distorted by a factor at most SD over epsilon. So basically, I'm going to show you as much as I can from the second step. So basically, how do we turn this weak embedding into strong embedding? And I will barely mention anything from the proof. I'll tell you what ingredients do we use for the first part, and in some sense it might be more interesting for computer science, like basically for people with computer science background. But unfortunately, in order to present the full proof of this first part, I need to introduce a bunch of hammers that we don't have time for, basically including some how to show communication lower bounds using information theory, all this like direct sum theorems and stuff like that. But I will mention some of these things on the next few slides. But then I will turn to giving you the almost like at least good chunk of the proof of the second part, how to turn a weak embedding to the strong embedding.
Could you quickly remind us what a linear embedding is? What makes a
right? It's just a linear map. So basically, like if you have mapping between normed spaces, it may or may not be linear, right? So it, like basically linear map as a map between linear spaces, vector spaces. So basically, it's just like, you know, f of x plus 1, f of x1 plus x2 equals to f of x1 plus f of x2. Kind of like if all your spaces are finite dimensional, then it's just, you know, like multiplying vector by a matrix. That's what linear embedding is. Okay, does it make sense?
Yep, thanks.
Yeah. Okay, so let's talk, before we dive into the proof of this geometric part, let's talk a little bit about information theoretic part. So that's our goal. So our goal, just like I'm reminding you the previous slide, so our goal is to cook a map that maps distances at most one into distances at most one and distances that are large into sufficiently large distances. And let me tell you what is much easier to obtain. Turns out that it's much easier. It's still not entirely trivial, but it's much easier to obtain almost what we want, but not quite. So basically we can obtain the map into L2 that maps distances. So the first condition is the same. Distances at most one get mapped into distances at most one, and distances at least d get mapped into distances that are slightly more than one. 1 plus 2 minus s, 2 to the power minus s, right? If we have a protocol with communication size s and approximation d. And moreover, this weaker statement is true not only for norms, it's true for general metrics. And it was used before our work by other people. But unfortunately, it's not good enough for us. We can't just use this easy statement and then upgrade this weak embedding into strong embedding. So we basically, the crucial thing that we need is we need a large gap between, so basically we need this gap between 1 and 10. So basically it should be at least large constant. I think it should be at least 8. And here we have, the gap is just like slightly more than 1, and it's exponentially small in the communication size. So basically that's why this easy statement is not enough, and we need to actually obtain 1 versus 10 on the right hand, in the image. That's why we need to work much harder. And again, we will have a proof by contradiction. So basically we want to say if there is a protocol, communication protocol for the distance estimation problem, then there is such and such map. And basically we will be showing that, assume that there is no map, right? So then I would like to show communication lower bound. That will be our way of proving it. So how do we show this? So we show that, suppose that there is no such weak map that maps small distances into small distances and large distances into large distances.
Sorry, then, just to make sure I'm understanding. So are you now proving the AK results with the exponential difference, or are you proving the
No, I'm not proving. Now I'm giving you outline of our proof. Actually, like I think this AK result is it's basically quite simple. So let me maybe say a couple of words. So the idea of for this easier statement is just do round elimination in your communication protocol and reduce it to just one round, and probability of success of this would be something like 1/2 plus 2 to minus s, something like this. And then basically, then one round protocol, you can turn to such embedding by just like spelling out all your probability space of like random coins and kind of like telling what message is being sent. Again, I'm like being extremely hand wavy, but you can actually like.
Oh, so the other player just basically guesses the message that was being sent. Is that
message is 1 bit, so basically your embedding
okay.
just becomes like whether the bit was 0. It's like easy to think about as embedding into Hamming space. So.
So remind me what was S again? Sorry then.
S is communication size, so it's like number of rounds, or you can assume it's like number of bits sent, but you can also assume that it's like S rounds, right, or 2S or something like this. So you basically eliminate all these rounds except one. So basically they just exchange 1 bit. And then whatever bit they exchange, you can just get an embedding out of it pretty easily. So that's what this AK and Andoni Krautgamer paper does. It's like lemma 1 in this paper, of course. Basically, then they do much more work for their main result. This is just a trivial statement that they show there. Okay, so but how do we obtain a stronger statement like what we need? So if we know that there is no good embedding, but basically the fact that there is a good embedding, you can encode as a certain convex program, right? So basically you just know that for every close points, your points in the image should be close, right? And for far points, they should be far. So this is certain semi-definite program, and we can take dual and basically obtain what's the condition which is equivalent to the absence of this weak embedding. Turns out that this is the following statement. And again, there is a little bit of subtlety here. You cannot just use like duality directly, because this is not even a finite SDP. It can be infinite. And for infinite convex programs, duality holds only with some caveats. It's not literally always true. But we can kind of like make it finite, kind of up to some approximation, whatever. It's not super important. Let me just say what we obtain. So what we obtain is, basically, we obtain two finitely supported measures, mu close and mu far, such that close measure is supported on pairs of points at distance 1, and far measure is supported on far pair of points, so at distance like 10 SD or 100 SD or whatever it was, from the condition of weak embedding. And then for every map from our space into unit ball of L2, basically, we have the following inequality. So basically, with respect to close measure, squared difference is not much smaller than a squared difference with respect to far measure, minus some slack. And so this is certificate of non-embeddability. Basically, implication in the opposite direction is easy to see. So basically, if you have such two measures, then you can easily conclude that there is no weak embedding, because like if there would be weak embedding, then you can take this embedding as F, kind of, and it would refute this inequality. But so like we show that we like basically the interesting part is this direction that is on this slide. So we obtain this two hard measures, close measure and far measure, with respect to which we have such inequality, and then how do we get this to communication lower bound? How do we show communication lower bound? First of all, we will show it for the wrong space, not for the space X we want, but for certain auxiliary space, and I will introduce this space now. Actually, interestingly enough, this implication was shown before by Andoni, Jerem, and Petrashko. So they showed that such a pair of hard measures implies communication lower bound for this auxiliary space. So what is this auxiliary space? So this auxiliary space is basically in this space. So it's like kth power of our original space with like L infinity in it. So what does it mean? It means that in the new space, the points are tuples of size k of the points from original space X, right? And how do we measure distance between two such tuples? Is we take distance between first components, distance between second components, distance between kth components, and then we take maximum, absolute, like maximum distance. That's why it's L infinity. So you can define in a similar way LP product and so on and so forth, right? But for us, we will be defining L-infinity product. And then, so basically Andoni, Jerem, and Petrashku show that if you have such a Poincare inequality, like I showed you on the previous slide, then your L-infinity, k-fold L-infinity product of X requires linear and K communication for distance estimation for approximation roughly SD. And let me give you a little bit of context, just historical context. So basically, this result is a generalization of disjointness lower bound from this paper by Bar-Yosef, Jairam Kumar, and Siva Kumar. So basically, this paper, BJKS, it kind of like introduced and developed the tool of information complexity for proving communication complexity lower bounds. And it provided a particularly nice and very conceptual and clean proof of that, you know, like there is this standard disjointness problem that Alice has a subset of some universe, Bob has a subset of some universe, and they would like to check if these sets intersect or not. And fairly intuitive statement that actually there is no better protocol than the naive one. Naive one is just like to send the set, more or less. And even for randomized protocols, you cannot do better much by more than a constant factor. And this was known how to prove before this BJKS paper. But the proof like they provide, it's very clean, very conceptual, and also it turns out that it generalizes to many other problems. So basically this Andoni, Jerem, Petrashku implication that this pair of hard measures implies communication lower bound for k-fold L-infinity product of X, it is a direct generalization of this Bar-Yosef, Jairam Kumar, Siva Kumar information complexity framework. I'm not going to talk about it much, but like I really recommend you reading this BJKS paper. It's like really, really beautiful and very instructive. And if you want to work in the communication complexity area, or like if you want to prove lower bounds for streaming, I highly, 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 highly recommend this paper. And this AJP reference, it's kind of like cute generalization of it that turns out to be exactly what we want.
Just so I can remind all the students, you know, we did talk about BJKS in this class. We didn't cover any of the proofs in it, but we used it as a black box, namely the fact that there is this communication lower bound for multi-party set disjointness. We used it to prove lower bounds for LP norm estimation for large P, or LP heavy hitters for large P.
Mm-hmm. Yeah, okay.
That's the same paper Ilya is talking about.
Yes, it's the same paper, but I'm referring to a different disjointness lower bound. The lower bound I'm referring to is just for two parties. But unlike the one that is Jelani talking about, where like, you know, for the multi-party disjointness, it's like first party sends to the second party, second to the third, third to the fourth, and so on. Here, we allow unrestricted protocols. So basically two parties can exchange any bits in any way they want. So it's kind of like two incomparable results, let me just say. And this paper has like a few more results. It's like very, very nice. Okay. And so we showed lower bound for the wrong space, but what can we say about our original space? So this is a kind of cute trick. Again, maybe let me not show it to you now because I want to spend quite a bit of time on the second part of the proof, on the geometric proof, how to obtain strong embedding from weak embedding. But let me just say that there is a simple trick that shows that actually such a lower bound that I have in the red frame here, so this one, it implies also lower bound for distance estimation in the X itself with communication S and approximation D. And roughly speaking, the intuition is the following. Again, it's a proof by contradiction yet another time. Suppose there would be a good protocol for X. Then turns out that I can obtain a sufficiently good protocol for this k-fold L-infinity of X. And basically, the reduction is the following. So there is a naive way of obtaining L-infinity K of X. Naive protocol is just like, let's use the protocol for X, but we will use it K times, right? And that's not what we want. So here, in order for this implication to go through, we need to, we may not lose in communication size, but it's okay to lose in approximation. So basically, we can't afford to run K copies of the protocol for X, but the trick here is instead of running K copies of the protocol for X, we will just run a single copy but instead of running it on like original vectors from X, we will run it on like folded vectors with random signs. Again, for the details, you can look at our paper, but like if you think about it a little bit, like I'm sure almost all of you will invent it pretty quickly. It's like a fairly cute but simple reduction. Okay, so now let me be more detailed. So I would like now to talk about geometric part of the proof, and actually I'll turn from slides to actually writing things, so that it would be easier for you to follow. Let me maybe switch now. So let me remind you what are we proving. So what I want to prove for you now is the following theorem. So basically the theorem says the following. Suppose you have a map from your space into Hilbert space or whatever, L2. I assume it's kind of L2. It doesn't have to be linear. And the map maps distances at most one into distances at most one and distances at least 100 SD. It maps into distances at least 10. So that's what I have. So that's what we obtain from the information theoretic part. So basically, remember, we showed that if such a map doesn't exist, then there is a communication lower bound. But because we have communication upper bound, then it means that this map exists. So what do we obtain then? So my goal is that existence of such F implies there exists linear embedding now it's linear, so let me call it, I don't know, G maybe, from X into L1 minus epsilon space for every epsilon, and the distortion as D over epsilon. So that's our goal of the remainder of the lecture. And okay, so essentially there are two big parts. Like I'll make this, so basically intuitively we take a map that kind of like nice on a single distance scale, so it kind of preserves a single distance scale, and then we obtain linear embedding with distortion that like, because it's linear and it has bounded distortion, it preserves all distance scales at the same time. But in some sense we give up a little bit because original map was in L2 and the final map is into slightly less nice space. It's like L1 minus epsilon. Okay, so how do we do this? So we do this into two steps.
Sorry, can I ask you one more question?
Sure.
You mentioned that you could get this log of dimension in there for L1. Is that just by setting epsilon to be 1 over log dimension and using Holder's inequality?
Yeah, pretty much. So basically we say that you can set epsilon to be sufficiently small, and also we use dimension reduction into L1 minus epsilon for subspaces.
Okay.
So we have linear embedding into L1 minus epsilon. So by dimension reduction result, we can assume that L1 minus epsilon is not too high dimensional. It's like poly dimension of X dimensional. And then it means that it's sufficiently close to L1. And then we optimize over epsilon and get this log dimension of X exactly. Yeah, like what you're saying.
Oh, you said poly X dimensional or poly dim X dimensional?
Yeah, poly dim X. Yeah, yeah.
Okay.
Actually, in fact, it's like the stronger result holds. It's like, so basically if D is the dimension of X, then you can do dimension reduction to D poly log D for L1 minus epsilon. But for us, it would be okay to have just poly D. Okay, so yes, this is correct. So basically, this result for about L1 minus epsilon implies result for L1. So okay, so let's show this. And basically, this consists of two big lemmas. So the first lemma, it makes the map somewhat nicer, and then the second lemma makes it even nicer and turns it into a linear embedding. So let's declare our intermediate goal. So intermediate goal is obtain basically F tilde, a map from X to a Hilbert space. By the way, I'm gonna write H for a Hilbert space, even though it could be different Hilbert spaces every time. Let me just like abuse the notation and not write everywhere like H, H prime, H2 prime, H tilde, H2 tilde. Like every single time I write H, it could be a different Hilbert space. Roughly speaking, it's always L2, just like potentially of like different cardinality of dimension. It's not going to be too important for us. Basically, like for us, just Hilbert space is a space where we can take dot products and yeah, they behave as you expect. So what does this F tilde satisfy? So the first condition is that F tilde of x1 minus F tilde of x2 it's at most 2 tau 1 x1 minus x2 square root. And second condition is if distance between x1 and x2 is sufficiently large, more than so let me call this 100 SD some other letter. Let me call it delta, just not to write this 100 SD everywhere. So basically, like this delta is a threshold for large distances. So then if my distance is at least delta plus 2, then distance in the image is at least tau 2 square root minus square root of 8 tau 1. So basically what did change compared to previous, compared to initial map? Basically now the second condition is kind of the same. So basically large distances get mapped into large distances. Nothing much changed. But the first condition became nicer. Not only we know that small distances get into small distances, we also have that we also now can extract some useful information about large distances, you know. Basically large distances don't blow up too much and small distances stay small. So we kind of regularize it a little bit. So that's our first goal. And now you can also see why I require tau, like, oh, sorry. Let me also, what am I writing? So let me also call these things tau 1 and tau 2. That's why I require tau 2 to be like at least 8 times tau 1 in order for the second condition not to be vacuous. And that's exactly why we need this sufficiently big gap between tau 2 and tau 1. Otherwise, this step just becomes vacuous and we cannot get anything from it. So let me show the proof to you. It's actually kind of not very difficult, but kind of cute and requires a few tools that I think you need to know about. And then I'm not sure if I will have time to show how to upgrade this map into a linear embedding, but at least I will try to outline the sketch of the result. Like in the best case, I will show you most of the proof. In the worst case, just like, you know, main steps. Okay, but let's see how to obtain this intermediate goal. So basically, this result is just a composition of two other results. So like let me give you these two facts. So the first fact is square root of Euclidean space embeds back into Euclidean space. So what does it even mean? Like, what the hell am I writing? So basically, if you have a Euclidean metric, or if you have like some subset of Hilbert space, in fact, if you have any metric space and you take square roots of it, so basically if you consider the same set, but all distances you take square roots of, it will still be a metric. It will still satisfy triangle inequality just because, you know, square root is a concave function. So it still satisfies triangle inequality. But we need additional stronger statement that if initial metric was Euclidean, then square root of it is also Euclidean. So it can be embedded back into Euclidean space with distortion 1. So you don't lose anything in the distances. And this is not a trivial fact. It actually is one of these results published by Schoenberg in 30s. The proof is not very difficult, but it kind of like relies on this theory of positive semi-definite functions, which by the way, we will see later in this lecture. And it's actually like pretty subtle. So it's not like obvious. The statement might look obvious, but the actual statement is also not obvious. If you think about it, even if your original metric is not just like high dimensional Euclidean space, but just a real line, and basically now you define a new metric on the real line, which is like square root of original metric, the fact that this embeds into Euclidean space, that's also non-trivial. And actually like general result follows from this one-dimensional result pretty easily. But one-dimensional result is tricky.
Actually, Ilya, so I have a question about this. So you mentioned if I take square roots, I still have a metric. I still have a metric, but not necessarily a norm space.
That's right,
like,
yeah.
Okay, because like C times X will not have the norm C times the norm of X.
Yes, yes. So in fact, this embedding is not linear, the one that I'm just mentioning, precisely for the reason that you said. So if you take like square roots of Euclidean space, then yes, you can embed it isometrically into Euclidean space, but it can't be a linear map because otherwise it would break homogeneity. Does it make sense?
Yeah, sorry, yeah, thanks.
Yeah, so this is the first fact. And second fact that we need is, so this is fact one, this is fact two. Basically, we will use certain extension theorems. So what is extension theorems? Okay, so the classic result, which we will not need, but what we will need is a certain variation of it. So classic result is a theorem of Kirsch-Brown. So Kirsch-Brown theorem says the following. If you have Euclidean space, so this is Euclidean space, and you have any set in it, it can be finite, it can be infinite, it can be measurable, anything, literally, it can be any set whatsoever. And suppose that you map this set into another Euclidean space, and this map is one Lipschitz. So what is one Lipschitz? It means that distances do not increase. Distances can only decrease between points under such map. So this is one Lipschitz. So then Kirsch-Brown theorem says that you can actually extend this map to the whole space. So now you can actually, like, if you have new point in this space that is not one of the original ones, I can define this map in a consistent way, such that the resulting extension is one Lipschitz as well. And it feels like, it feels like kind of useless result. Because of course we have lots of room, right? We can define this function on red points in whatever way we want. How come this is, first of all, non-trivial, and why this is useful? None of these questions is easy, but it's actually like, it's not a difficult theorem, but it's kind of cute, and it also uses duality in some nice way, convex duality. Why this is useful, we will see later in the lecture, like we will see very soon, in fact, that certain variant of this extension theorem is useful. But let me just say that there are many known extension theorems, and two of them that I will have mentioned. One of them is Kirsch-Brown, another I'm about to mention now. This is just, scratching the surface. There is like whole subfield of geometry which is concerned with like extension theorems. So the specific extension theorem we will need is the following. So suppose that instead of Euclidean space, original space is general metric space, right? So now instead of Euclidean, we have general X. And your map is still defined into Euclidean space. So can I obtain the same result? So can I generalize Kirsch-Brown theorem, but when domain is general metric instead of Euclidean space? Turns out that you cannot, and there are known counterexamples. I think it's even false when X is just L1 distance. But what you can show instead is extension theorem where instead of one Lipschitz maps, we consider 1/2 Hölder maps. So let me explain what this means. So basically 1/2 Hölder condition. So we say that this capital F is 1/2 Hölder is if f of x minus 1 minus f of x2. So norm is at most some absolute constant times square root of x1 minus x2. So this is a weaker condition than Lipschitzness. Basically, like these are incomparable theorems because we assume less about our function that it's 1/2 Hölder, but then we make it work in greater generality that like instead of Euclidean domain, you can have any metric space whatsoever that you want. And in fact, proof of this theorem is not very different from Kirsch-Brown's theorem. It's also like duality. In our paper, we have like reference to a classic book where you can actually find nice proofs of both of these theorems and way more. So these are the two classic facts that we need. So basically, square root of Euclidean space can be also realized as a Euclidean space, and we need this variant of Kirsch-Brown theorem that says that any 1/2 Hölder map defined on a general metric space into Euclidean space can be extended to the whole space. Originally, it's defined only on a subset, sorry, and subset can be anything. So okay, so let's prove our theorem. Let me remind you what the theorem was. It's actually not a theorem, it's this intermediate goal. So basically, I would like to construct a function from my space into Hilbert space that long distances maps into large distances and maps into large distances. And basically, it is also 1/2 Hölder on the upper bound side. So, okay. I mean, you see this like 1/2 in the exponent, that's not a coincidence. That's exactly why actually we need both of these statements. So the proof is the following. So we take our original map, F. So F is our like weak embedding. And then let's prove the following very simple observation. So claim. So basically, our weak embedding, it maps short distances into short distances. It maps distances at most 1 and the distances at most tau 1, right? So basically, this allows us to derive a corollary that for every x1 and x2. So basically, intuition here is that on large distances, f behaves Lipschitz in a Lipschitz way, namely f of x1 minus f of x2 is at most maximum of 1, 2 times x1 minus x2 times tau 1. Okay, so let's first of all parse what the hell did I write? What the hell I just wrote? So if distance between x1 and x2 is tiny, then this statement just says that, like if distance between x1 and x2 is very small, then the distance between f of x1 and f of x2 is at most tau 1, right? That we know already because this is just part of definition of a weak embedding. But this statement becomes interesting when distance between x1 and x2 is large. So if distance is large, before we didn't know anything on the upper bound side, and now we know that, it's like kind of Lipschitz with constant 2 times tau 1. And by the way, why this is true, it's very simple. So basically, if you just take any points that are sufficiently far, x1 and x2, you take the segment between them, and then you split it into equal parts of size 1, right? Up to a rounding error. And then you just apply the fact that distances at most 1 get mapped into distances at most tau 1, and then we just use triangle inequality, right? Why we lose this factor of 2 here is precisely of this rounding error. So what if distance between x1 and x2 is just like a little bit more than 1, but then we have to have like 2 segments, right? So yeah, so that's the whole proof of the claim. And now let's just apply our first fact. So let's just use the fact that square root of Euclidean space can be mapped into Euclidean space. So it means that we can get a new map, which we call f tilde, f tilde, that is from X into Hilbert space, such that yes. So basically, we can take square roots of Euclidean space and realize that as Euclidean space. So we can take this large-scale Lipschitz condition that is written here, and say that for the new map, it holds with square roots. So namely, f of x1 minus f of x2 is at most maximum, so f tilde maximum of 1. Then we have 2 times norm of x1 minus x2 square root times square root tau 1. And then the second condition for now we just take from the definition of a weak embedding. We say that if distance between x1 and x2 is at least d, then the distance between images is at least square root of tau 2. So for now, I just used this claim and the fact that I can compose this map with a map that embeds square root of my Hilbert space back into another Hilbert space. Okay, so now it's time to use my extension theorem. So what do we want? So why we are not done yet? So second condition is kind of what we want. So large distances get mapped into large distances, but we know nothing for small distances. So if distance between x1 and x2 is very small, sorry, I should have written tildes here. If distance between x1 and x2 is very small, then the first condition gives us nothing, but we want to obtain some Hölder condition that we later want to use. So for this, we need an extension. And the extension theorem, actually, we use in a very simple way. So we take our space X, and we find a net in it. So this is one net. So any point is within distance 1 from n. And at the same time, points in n are 1 separated. So you can construct such a net using greedy algorithm. So here we need to be careful because our net can be infinite, but it can still be done. At least intuitively, it should be clear. So now we take our map f tilde and just consider its restriction on the net n, right? So the nice thing about this restriction is that now it's 1/2 Hölder. And this follows from our claim 1. So basically it follows from this first condition. Because if points from the net are different and net is 1 separated, then actually maximum will never be 1 and maximum will always be the second term. So it's 1/2 Hölder with constant square root square root 2 times tau 1.
Sorry, did you define net on the previous slide? Just a warning that I've never used that word yet in this class.
Oh, yeah. So, okay. So let me say what this means. So we choose a subset of our space such that, so it's basically just like notion of epsilon net. Basically, any point from our space is within epsilon, in this case, epsilon equals 1, within distance 1 from some net point. So basically, balls centered in points of n of radius 1, they cover the whole space. And at the same time, the second condition that we want is that distances between any 2 points in the net, they are more than 1. And you can always construct such a thing for any metric space. For example, if your space is finite, then you can just, if some point is not covered, just take it as a center of the new ball, remove the ball, and recurse. For infinite case, you need to be slightly more careful, but it can be done as well. So you kind of do it for larger and larger ball, and it works. So the point is, because the net is 1 separated, our f tilde function that we defined on the previous page, restricted on this net, it's 1/2 Hölder with constant square root of 2 tau 1. So now we have this 1/2 Hölder function. We can use our extension theorem. So we extend this f tilde to a function g defined on the whole x. And what conditions do we know? So restricted on the net, it coincides with f tilde restricted on the net. And second, this g is 1/2 Hölder with constant square root 2 tau 1. And the second condition is a big victory for us. Why is that? So this is great, because that's exactly what we wanted. So remember, that was our intermediate goal. And this is exactly the first condition of this intermediate goal. So now it is enough to check that we have also the second condition. So basically, now because we took a function that maps large distances into large distances, but then we kind of like, lost all the information about the function except values in the net, and then we used extension theorem. So why do we still have that large distances get mapped into large distances? That's not very hard to see. So basically, the intuition is that if you have two faraway points, then you can find net points that are like within distance 1 from these 2 points. Then on these net points, functions stay the same. So we have the condition that basically distance between images of net points is still large. But then we use also that the function is 1/2 Hölder. So we have that basically these distances did not blow up too much. So I'm not going to write this, but this gives us exactly what we need in the end. So it gives us basically this condition. So precisely we lose this +2 because of this net rounding argument, and we lose this here a little bit also, like precisely because of this triangle inequality. Okay, does it make sense? So our intermediate goal we proved, give or take. Okay, so now let me, in the remaining 24 minutes, let me tell you as much as I can about how we take this new function f tilde and upgrade it into linear embedding into L1 minus epsilon. So it still feels, we're not quite done, right? So first of all, this embedding is not linear. And second, sure, our upper bound became somewhat nicer, but lower bound is still just for a single distance scale. So how do we deal with it? Okay, and here we will use the power of Fourier analysis. Here is how. So let me formulate a statement that we are proving. This is again just like slightly different, just simplifying the notation a little bit, but basically the statement that we need to prove is the following theorem. Suppose that you have a function from X into a Hilbert space, and suppose that f of x1 minus f of x2 is at most absolute constant times square root of x1 minus x2. And if x1 minus x2 is large, then distance between x1 and x2, images of x1 and x2 is also large, say at least 1. Then I would like to prove that there exists a linear embedding from X into L1 minus epsilon with distortion something like delta over epsilon. So that's my goal for the remainder of the lecture. And this would conclude the proof of our theorem. So, okay, so here is what we need to do here. So again, we need a few facts. Let me introduce them as we go. So the first fact is that if you have a Hilbert space, you can always map it into another Hilbert space with the following properties. Basically, dot product between images of this embedding is exactly equal to E2 minus squared distance between three images. So this again uses this theory of positive semi-definite positive definite functions. So again, this is like classic result of Schoenberg, and again, this is not easy, and the map is like very non-trivial to construct. Actually, like one thing to notice here is that this is not just a map into Hilbert space; it's in fact a map on a unit sphere of of your space. And why is that? Because, you know, if h1 equals to h2, then dot product is equal to 1, right? So it means that length of every vector in the image is exactly equal to 1. So we do map onto, well, not onto, but we map to unit sphere in H prime. So let's take this map G and compose it with our map F. So let's define a new map F tilde, which is just composition of G and F. So what do we know about this map? So let me write the conditions here.
Oh, this fact F1, I feel, is that something that people use a lot in machine learning?
Yeah. I mean, as you will see, what I'm gonna talk about now, it has to do a lot with all these kernels and stuff like that. So yes. In particular, I think, okay, let me not say anything on the record. So yes, of course. Okay. So what do we know about this composition? So basically, it's just the same conditions as before, but now instead of distances, we have dot products, right? Just because we, you know, like we turned distances into dot products by using this map G. Yes, this is like feature representation of whatever Gaussian kernel or something, right? Is that what you're referring to?
Yeah, I think so. I forgot the name, but it sounds.
Yeah. Okay, good.
Radial kernels or something.
Yeah. Okay, good. So so what do we know? We know here that you know, like dot product between f tilde of x1, f tilde of x2 is at least e2 minus k x1 minus x2. So we had square root, but because we have square, now we have first power. And if distance is at least delta, then the product is at most 1 over e. So this is just rewriting, nothing much is happening. So now we're going to use the fact that, you know, like we'll use characterization of dot products. So basically, if you have any set with pairwise values on it, so like kernel, so kernel can be realized as a dot product in some Hilbert space if and only if it's like symmetric positive definite kernel. So what does it mean? It means that, you know, we have a function k like x1, x2, and it's like non-negative, symmetric, and positive definite just means that if you take any endpoints in your space and form a matrix k of xi, xj, this matrix is PSD. And this is if and only if, in fact. So in one direction, it's obvious. If you have dot product, clearly it has this property. In the opposite direction, it's like also true. You just need to work a little bit. Also like one of the classic Schoenberg results. Basically, it's like really like sponsored by Schoenberg, this part of the talk.
I mean, is that the same thing as the spectral theorem, or is?
I'm not sure. I'm not sure it's the same. Spectral theorem, I think, says a little bit more. This is, but I'm not sure. So let's not argue about it. We don't have too much time. But it's not a hard result. So okay. So now there is a one step whose proof I will not show you, and both because it's not very like enlightening proof, and because it's like not very interesting part of the proof. So the second step is to actually say that. Okay. So basically, previous conditions from the previous slide, previous page, tell us that there exists a kernel that satisfies certain properties, right? Just because this embedding f tilde gives us some condition on the dot product. So next step is to say that actually, without loss of generality, we could have taken this kernel to be shift invariant. So basically, we can assume that our kernel x1, x2 satisfies that it's like phi of x1 minus x2. So then what does it mean in terms of conditions on the phi? What do we have? So we have that like phi of 0 equals to 1. So phi is a function from our space into real numbers. Phi of x for any x is at least e to minus k times norm of x. And if, so this is second condition, and the third condition, if norm of x is at least delta, then phi of x is at most 1 over e. Why can we always do that? We need to do certain symmetrization. We need to take our kernel and apply certain averaging procedure to obtain shift invariant version of it. But the annoying thing here is that we do averaging over some like not some obvious distribution, because there is no obvious distribution on x, right? But we need to do some kind of like, basically this averaging requires some axiom of choice, and it's a certain crazy object that we need to use for averaging. It's called like so-called bounded shift invariant mean or something like this, and it requires axiom of choice to build, but it can be done. So we do obtain this positive definite, now it's called positive definite function, because it's like positive definite kernel, but like shift invariant. And this positive definite function has these properties. In 0, it's 1. Close to 0, it's not too far from 1. So in particular, it's continuous in 0. And sufficiently far from 0, it decays non-trivially. So basically, like if you step away delta from 0, then your function is always smaller than 1 over epsilon. Sorry, 1 over e. So it's smaller than some constant, whatever. So now we can use what's called Bochner's theorem. So what is a Bochner's theorem? Bochner's theorem is a classic fact, actually not very hard also to prove, that says that like it exactly characterizes set of all possible Fourier transforms of random variables. So if I have random variable on d-dimensional space, I can consider its Fourier transform. I will say in a second what it is. And then turns out that by Bochner's theorem, set of such Fourier transforms are exactly positive definite functions that are equal to 1 in 0 and that are continuous in 0. And this is exactly what we have here. So by Bochner's theorem, we obtain that there exists a distribution mu over, let me write it this way. Let me write it like r to the power dimension of x. I could have written x, but it would be a little bit misleading to write that it's defined on x. It's defined in some sense on the dual space. But let's not worry about it. Let's just say it's d-dimensional space where d is dimensionality of our original norm space. So there exists a probability distribution over this space such that its Fourier transform is phi. But what does it mean? It means that for every x, expectation over some additional vector sampled according to this measure is of this Fourier harmonic is exactly equal to phi of x. So we kind of take inverse Fourier transform and obtain certain probability distribution. So, okay, so now we are very close to be done, at least in terms of stating what our embedding is. Let me maybe state what the embedding is. I don't think I will have much time actually to prove the quality of it, but let me just give you the intuition. So the intuition is that this distribution mu turns out that it is a decent linear sketch of x. So what do I mean by that? So let me actually state a certain lemma on the quality of this distribution. So like which properties do we want? So we have that for every x in x. Basically measure mu of the set of vectors v such that dot product between x and v is at least norm of x over delta. So this probability is at least some absolute constant, positive constant. And then the second statement is for every t larger than 0, probability of all the vectors such that dot product is not too large, so it's at most t times norm of x is at most 1 over t. So let me parse what's written here. So what I'm saying is that if you take any fixed vector in my normed space and you sample a random vector according to this probability measure mu, then dot product would not be too far from the norm of x. So namely, dot product with decent probability would not be much smaller than the norm of x. And for the upper bound side, we have a whole tail. So basically like probability that is like t times, so we kind of show a Cauchy tail kind of thing on this dot product between x and v. So it's kind of a linear sketch. It's one measurement linear sketch for x. And after we establish this lemma, the resulting embedding is actually pretty easy. Let me tell you what it is. And then maybe I'll say 2 words about proof of this lemma, and maybe I will even not. But so the resulting embedding of x into L1 minus epsilon is the following. So I want to embed x into L1 minus epsilon. So let me define what my L1 minus epsilon space is here. So it's a space of functions. So basically in the original space, I have points x. So this is my, this is space of functions. And functions are defined on from actually again like r to the power of dimension of x into reals. And let me tell you the mapping. The mapping is very simple. We map x into, so like maps to. So now I need to define a function that takes a vector from here and obtains a real number. And the function is very simple. V gets mapped into dot product of v and x. And so this is the embedding. It's like almost disappointing, but the interesting part, of course, is that we need to use mu in some way, right? So basically, when you define like LP space, you also have some measure with respect to which you integrate. So like basically here, underlying measure is mu. So let me explain you what I'm talking about, like what am I writing here. So basically, L1 minus epsilon norm in the target space is defined as follows. So, so let me call this mapping capital F, and then my capital F of x L1 minus epsilon norm would be just integral over my d-dimensional real space of dot product between v and x raised to the power 1 minus epsilon. I integrate with respect to measure mu, so I have like mu of dv, and then I need to raise everything to the power 1 over 1 minus epsilon. So this is my L1 minus epsilon norm. And then actually like using these 2 conditions that I promised you in this lemma, you can actually show that this integral doesn't deviate too much from norm of x. Lower bound is pretty trivial. You just use the first condition and, you know, just say that in a significant part of the space, this dot product is sufficiently large and we are done. So upper bound is a little bit more delicate. Actually, like because of this upper bound, we cannot obtain, for example, embedding into L1. So we need this 1 minus epsilonth moment precisely because we have this Cauchy tail. And if you know about your random variable that it has Cauchy tail, it doesn't even have to have expectation, right? But it always have this like 1 minus epsilonth moment. And that's why we have something nice and bounded there. So yeah, that's the embedding. And let me say maybe a couple of words in the remaining 6 minutes about how do we prove this lemma, because I think it's pretty nice. There is no magic here, really. So it's just you need to be. So we use the following facts about Fourier transforms of random variables. So first of all, what can we even use, right? So we need to use these conditions. So we remember that our measure is not just some measure, but it came from positive definite function that has these properties. It's like sufficiently continuous, quantitatively continuous around 0, but then it like at the infinity it kind of like decays, or at least it doesn't decay, but it's not like too close to 1. Okay. So yeah, so basically the statements that I'm gonna use, basically it's convenient to, okay, so if you have a random variable, and if you take dot product of this random variable with a fixed vector, like we do, so we always fix this x from x once and for all. And if you take dot product of random variable with a fixed vector, then in terms of Fourier transforms or characteristic functions, it just means that we take a restriction of our characteristic function on a line that passes through x. So basically we have our d-dimensional space, and we have like vector x. And then if I take random vector v and take dot product between v and x, then Fourier transform of this dot product is just, so it's like psi of t. It's like Fourier transform of t times x. Sorry, Fourier transform of the original distribution in the point t times x. That's just a simple check. So we basically reduce our problem to question about one-dimensional random variables and one-dimensional characteristic functions, like Fourier transforms. And then we need two facts. So we need the following claim. It's almost a reformulation of what we want, you know, like if this psi in the point delta is sufficiently small, so it's like less than 1 over e in this case, then, okay, let me, I think I don't have time to properly explain it, so I don't want to botch it too badly. So let me maybe just say a few words here. So, okay, so intuition is that one of these conditions follow from, so basically the first condition follows from the second condition here. And the second condition follows from the first condition here. And these are like simple calculations. So I unfortunately I don't have time to show it to you, but you can actually check it. It's not very hard. It's written in the paper. In fact, it's like standard in the probability literature. So there is nothing groundbreaking going on there. Yeah. Okay. So that's it. I think I'm done. I'm almost perfectly on time.
All right, thanks a lot, Ilya. And by the way, that other theorem that you had on the slide for a little bit, Bachner's theorem, that's the thing that I had in mind. I know random Fourier features by Rahimi and Recht for kernel approximation, I think is based exactly on Bachner's theorem.
It's exactly, what I didn't want to go on the record with, but yeah.
Oh, okay, I see, okay. Okay.
Yeah. It's all very related. Yeah. In fact, I think it would be nice to kind of compare some of this geometric literature that uses this like inverse Fourier transform for computing these embeddings and this machine learning literature. I think there are some parallels that people just didn't even notice or don't even care about or something. I think it would be nice.
All right. Thanks a lot, Ilya. I guess let's give him a round of applause. Feel free to unmute yourself, everyone. Yes, it takes time for people to unmute themselves.
Okay, yeah,
there's a way that I can quickly unmute everyone.
Just wanted to say that if you have any questions, I guess it might be that you have more questions than answers. Feel free to look at our paper. Feel free to email me. Basically, I'm happy to tell you more. Just like within 1.5 hours, it's not very easy. So.